Okay, well, it's a great honor to be speaking here on the occasion of celebrating Spenta and his contributions to science and institution building. Much of my work the past year has been on entanglement, and I think perhaps for that reason the organizers put me in this session. But I already spoke on entanglement at the Indian Strings meeting in December, and then there was a meeting of the IT from Qubit collaboration to which I was kindly invited, and I spoke there in Stony Brook where some of you were there. So I thought maybe let me tell you about something else I've been doing, which is also kind of fun, and in fact brings together different kinds of physics. That's always been something that Spenta has been happy to emphasize and do in his own work. So the topic is anisotropic geometries, viscosity, and cold atoms. I'll begin with an introduction, tell you a little bit about anisotropic geometries in the context of ADS-CFT, give you one rather simple example which will then lead into the rest of the discussion, then tell you about how viscosity behaves for systems which admit these anisotropic geometries as dual descriptions. And it turns out that the viscosity can do something really quite different from the isotropic case, and it can do this in quite a generic way. As you all know, in the isotropic case, if you have a system with a smooth gravitational dual, then the viscosity satisfies this famous result that eta over s equals 1 over 4 pi. But in anisotropic systems, quite generally, as you'll see, some components of the viscosity in units of the entropy density can become very much smaller than 1 over 4 pi, parametrically smaller than 1 over 4 pi. And in fact, this will turn out to be a very general result that we will be able to derive from gravity. Now, since it's such a general result that comes out of gravity, it prompts us to ask the question, can it possibly be observed in nature? Of course, we don't have gravitational duals of systems we can actually observe in nature. But given that in the isotropic case, one has found, for example, in the Rick experiment and in cold atom experiments that eta over s is quite close to this bound that comes out so beautifully from gravity, 1 over 4 pi, it prompts the question, can this very general qualitative behavior that comes out for anisotropic systems from gravity also be seen perhaps in experiments? And so in the last part of this talk, I'll tell you about experiments that we have been thinking about, and this work is in collaboration with a colleague of mine at TIFR, Rishi Sharma, who actually works on cold atoms and so on, so he's a real expert, which is the only reason I have any confidence in what I'm going to tell you for the fourth part. But it'll turn out, and I'm really quite excited about this, that if you look at the existing cold atom experiments, just by driving them into the anisotropic regime, given the kind of things they've already been able to achieve, the kind of time scales and sensitivities they have, they should be able to see. If nature is kind and gravity results tell us something about what happens in these experiments, they should be able to see the fact that the viscosity tends to become smaller than this number, 1 over 4 pi. Okay, and then I'll end with conclusions. So as you all know, it's a famous result in strongly coupled field theories dual to a smooth geometry. For example, the n equals 4 super Young-Mills theory, which is dual to ADS5. We know that the shear viscosity over the entropy density equals 1 over 4 pi. This is a result which was derived by Kovtuns on starinets. Actually goes back earlier, as you all know, very nice paper by Shumit Das, Gary Gibbons, and Samir Mathur, who showed there was a universality to the black hole absorption cross-section, which essentially, when you convert it into modern day parlance, is this result. Earlier work on the membrane paradigm and so on. But anyway, it really was brought to light by this work of Sohn and collaborators. And in fact, KSS suggested that this might be a bound, okay, as to how small the viscosity could become. If you do a weak coupling calculation from Boltzmann transport, you get that the viscosity over entropy density is the ratio of the mean free path over the de Broglie wavelength up to, with some coefficients here which are constants. There's a mean free path because this is a transport parameter, and the other thing that comes in is the de Broglie wavelength. And they suggested, look, at weak coupling, the mean free path, of course, will be bigger than the de Broglie wavelength. But as you go towards strong coupling, what can happen? At most, the mean free path can become of order the de Broglie wavelength. It can't become smaller than that. And so therefore, they said maybe at strong coupling, it saturates to some number of order 1. And why not? Maybe that saturation is achieved by a smooth Einstein gravity system. Okay, and that was the suggestion. We now know that that is not the case. You can add higher derivative corrections in a legitimate way to the two derivative Einstein-Hilbert action, and that can drive the viscosity to be smaller than 1 over 4 pi. But in all controlled examples of this kind, the resulting corrections are small. Okay, we can't go to a genuine limit where these corrections are order 1, as far as I know, and do a calculation. So we know that it's not a bound, but maybe there is still a bound, just not quite 1 over 4 pi. Maybe the viscosity can't become very much smaller in the isotropic case. Certainly, or maybe Igor has his hand up. Yeah? I don't remember this, sorry. I see. Because weak coupling, of course, eta will be very big compared to, I'm sorry, I don't know that. Maybe I can look at it. So me, as far as I know, I don't know. I try to ask around. No known example is known in nature which violates this bound. Again, maybe somebody more familiar with nature will correct me, but that's what I've been told. Okay. Okay, so far we are talking about the isotropic case. Now let's go to the main part of this talk. Now it turns out, as you'll see in anisotropic systems which do admit smooth gravity duals, you can often have a violation of this bound and some components of the viscosity, because when you're in an anisotropic system, the viscosity really should be thought of as a tensor, and in general the shear viscosity turns out has 21 independent components, so it's a bit of a mess. We'll not work with the most general situations, so it'll still be more manageable, but some components of the viscosity tensor in fact become much smaller than the entropy density, and for example, this behavior can go like the temperature over the anisotropy parameter to some power, and if you go therefore to the highly anisotropic regime where the temperature is much smaller than the scale which determines the anisotropy, this can be parametrically smaller than 1 over 4 pi. Okay? So that's what you'll see. Now, so let's talk a little bit now about anisotropic geometries. Now, in fact, the very fact that anisotropic geometry should arise, say in the context of ADS CFT, is at first sight perhaps a little confusing, because to the extent you think of these geometries as the neo-horizon geometries of black holes, the no-hair theorems, which we have known about for a while, might suggest that in fact these kinds of anisotropic situations should be very hard to find, even maybe impossible, because after all, the no-hair theorems tell us is that the structure of near-horizon geometries is very robust. On the other hand, of course, we know there are many, many phases seen in nature, and therefore we expect, it's expected that many such phases arise in strongly coupled systems, and then therefore ADS CFT would suggest if these phases have gravity duals, that perhaps this expectation from no-hair kind of considerations is not correct. And in fact, that turns out to be true, and this is an old and long beautiful story now, and the key, I think, is that asymptotically ADS space is different from asymptotically flat space, and that is why, for example, you can have scalar hair and you can have holographic superconductors, and that is also why you can have actually a lot of structure in these kinds of asymptotically ADS spaces, which can also be anisotropic. Okay, and in fact, this is an aside, but I'll give you one of my favorite examples because it's also an example of different ideas coming together. So, for example, in cosmology, so you may ask, what is a general space-time which is homogeneous? Homogeneous is a generalization of the idea of translational invariance, so which is homogeneous but not isotropic. And in fact, this is a question which has been much studied in cosmology, and Bianchi classified the most general such cosmologies in the past, and he had a symmetry-based classification with 9 kinds of groups. And it turns out that you can realize many of these Bianchi types, okay, in the context of an asymptotically ADS space with very reasonable matter, gravity, gauge fields, scalar fields, and you can realize type 2, type 3, type 5, type 7, type 9 in very simple systems. And so that tells you the kind of sort of, structures you can get. And these, I think, might be of interest in the study of strongly coupled field theories, say, I don't know, liquid crystals or something. It's an area which has not been, I think, explored very much. Okay, that's an aside just to tell you we can get anisotropic geometries of many interesting types. But now what I'd like to do is study a very simple anisotropic geometry because our focus here today is mostly on viscosity. So just consider the following very simple system. We are in 5 dimensions, Einstein gravity, negative cosmological constant, and a scalar field. So studied also with Anindya, who I'm not sure he's here. Of course, this has a well-known ADS5 solution where the dilaton is not, the scalar, let me call it dilaton, is not excited at all. But now let me consider a solution where the dilaton is excited, and let me take it to be linear in one of the spatial directions, z. Rho is now a parameter that determines the anisotropy. This breaks rotational invariance. It turns out that now the metric you get by back reacting is more complicated. This turns out to be an exact profile for the dilaton. It solves the equations of motion consistently because it's so simple. And the resulting geometry now is the following. Asymptotically very far away, the effect of this scalar field dies out and you get ADS5 again. But as you go in towards the horizon, the geometry departs and in fact becomes ADS4 cross R. So here we are asymptotically ADS5 going in, it becomes ADS4 cross R. The extra stress energy that the dilaton gives prevents one of the directions, the Z direction, from contracting. So the other directions contract as you go towards R equals 0. That's away from the boundary, but the Z direction stops contracting, okay? And so this is ADS4 cross R. So it's a very simple kind of attractor geometry that you end with in the infrared. Now you can see that this breaks the spatial rotational symmetry down from SO3 in ADS5 or in the boundary theory to begin with to SO2, which has to do with the fact that you're driving the system with the scalar field, okay? Also, the scalar field, of course, breaks translational invariance also, but really you should think of it as the field theory being driven by a force which is proportional to the gradient of the dilaton. You can make that more precise by computing the stress energy tensor equation, which turns out to be d mu t mu nu is the gradient of the dilaton times the expectation value of the operator, dual to the dilaton. So here we have a driven system, and you have anisotropy in the driving force, and it's behaving in this manner with ADS5 becoming. What you can similarly have is stress energy which diffuses, in the sense you can have a fluid, and this will be relevant for us, which is moving in the x direction, but with a velocity which changes in the z direction. And if you do that, then you can have a shear, you can then have a shear in the system because the motion is in the x direction. That's the Goldstone mode because you have residual Lorentz invariance, but that velocity can change in the field. Okay, that's interesting. That's interesting, maybe. Okay, let me go on. So in a situation like this, because you at least have residual SO2 symmetry, the viscosity can be broken up using these symmetries into a spin 2 component, a spin 1 component, and a spin 0 component. Let me focus on the spin 1 component, and I denote that by either eta xz or eta yz. Z is the anisotropic direction. What I mean by eta xz is what you would obtain from the 2-point function response of the xz component of the stress energy tensor, okay? And similarly for yz, the spin 2 component you would obtain from the Kubo formula involving Txy, and I denote by xy, eta xy. Okay, now what happens if you compute the viscosity? So the viscosity at at small anisotropy where the temperature, so now you can heat the system up. I told you it was ADS5 going to ADS4 cross R, that's at 0 temperature. Now you can heat the whole system up, easy enough to do. When the temperature is much bigger than anisotropy, you expect the effects of the breaking of rotational invariance to be small, and eta over, sorry, this should be 1 over 4 pi, excuse me. Eta over S is 1 over 4 pi minus some positive constant rho square over T square. Okay, so already you start seeing the effects of the viscosity becoming smaller than 1 over 4 pi to second order in this driving force. To first order in the driving force, what happens simply is you have the isotropic fluid, which is driven by a driving force and it responds to it in that way. But to second order, the geometry itself begins to get corrected because of the stress energy. That is to say, from the field theory point of view, the equilibrium phase configuration begins to change, and therefore the viscosity itself changes to second order in the anisotropy. So this is what happens. Now the interesting thing is if you go to extreme anisotropy, then in fact you get this behavior where eta over S now becomes very different from 1 over 4 pi and much smaller, okay, parametrically small. On the other hand, the spin 2 component continues to be 1 over 4 pi, okay. All right, how general is this result? Well, other examples were known even earlier than our work by Reban and Steineder. I forget when, but soon around the time we did our work, Polchinski and Silverstein wrote a very nice paper where they had a supersymmetric example. So there was no issue of stability and so on. We tried to study the stability a lot also, but they had a supersymmetric example showing the same kind of behavior, etc. And in fact, what one could show, we showed in a subsequent paper, is that this is really quite general. Namely, let's take a system where you have an external driving force which preserves translational invariance but breaks rotational invariance. And we kept translational invariance intact just because then transport is easy to think about. You know that the system breaks up into modes of different momenta. You first take the zero momentum limit, etc. So keep translational invariance intact. Then one can show very generally, and this is a very beautiful result, that eta over S for say the spin 1 component is given by a ratio of the metric components at the horizon. The metric component in the XX direction over the ZZ direction, okay? And remember what was happening when you had this ADS5 going to ADS4 cross R is that the X, Y directions continued to contract, but the Z direction stopped contracting. And that meant when you heated the system up to finite temperature, you got some finite value for GXX, but that could be much smaller than GZZ, because this is prevented from shrinking only by the temperature. And that is why you get then a behavior like some power, in this case, second power. In other systems, you may get other powers, but it can always, at small anisotropy, at small temperature compared to anisotropy, this can always become very small, okay? So that was a general result that came out quite generally. And now going to the last part of my talk, since it's such a general result, it prompted us to ask the question, okay, can you see it in nature? Now, of course, as I said, you have to be lucky, okay? The kind of systems you realize in nature are not at all those which are described directly by holography. But if you look at, for example, some of the cold atom systems which have been experimentally observed, in the isotropic case, eta over S is not 1 over 4 pi, but 6 times 1 over 4 pi or so. So not so far away from this magic number in string theory. That prompts us to ask, what happens if you incorporate this anisotropy? So here's what these systems look like. They're very funky. 10 to the 6 atoms packed together in a micrometer. Very cold, 10 to the minus 5 degrees Kelvin. Extreme regime of quantum effects coming into play. Lots of funky lasers, magnetic fields to excite the correct Feshbach resonances and so on. I don't know that much about it. We'll consider fermionic systems, so lithium-6 in particular. And there is a weak van der Waals force between the various atoms in these systems. This is a very complicated phase diagram, but I'd like to you to focus first at 0 temperature, which is here. Roughly speaking, there's an attractive potential between atoms, and the strength of that potential becomes bigger, so the potential well gets deeper as you go to the left. So if you're right here it's more like a BCS kind of superfluid. The atoms form a Fermi surface and there's weak pairing at the surface of the Fermi surface. As you go towards here, you go into the BEC phase, the attractive potential gets deeper, so the atoms form molecules which are bosonic, and the bosons then condense, okay? So this is a BEC kind of description, this is a BCS description, and in between, you have a point where the potential is such that you get exactly a bound state at a threshold. The scattering length diverges, so 1 over A in units of kf goes to 0, and that is the system which is then scale invariant, and which is what's called a Fermi gas at unitarity, okay? And this is the system which, when you then probe close to its phase transition, so now you take the system and you further heat it up, and when you heat it up, it makes a transition from the superfluid phase to the normal phase, and at that transition point, the viscosity, as I said, is not quite 1 over 4 pi in the isotropic case, but 6 times 1 over 4 pi, not so far away, okay? And in our setup, when we discuss it, what we will be doing is moving up and down along this line at unitary, okay? So that's the system, and as I said, it's strongly coupled with a viscosity not so far away. And the question is, okay, let's assume nature is a little kind. Can you at least set up an experimental test this propensity for the viscosity to become small due to anisotropy? Can you propose something? This is with Rickmoy Samanta, my student, who really wanted to push the consequences from gravity to connect with the real world. Rishi Sharma, who's an expert who works on, my colleague at TIFR who works on cold atom systems and so on. And the bottom line is, with all the caveats, that actually it's quite promising, in that it's well worth, we want to suggest to experimentalists that it's well worth their trying to look for that, for this kind of a feature, okay? Now the caveats, of course, are, first of all, look, no one's claiming, we are not claiming we have a gravity dual for these kind of experimental systems. And also, as you'll see, we can't quite drive the system to extreme anisotropy, only to anisotropies of order 1 and so on. So with all those caveats, it's well worth looking. All right, what's the idea? How do you introduce anisotropy? It's very simple. Anyway, they put these systems in traps. And so all you do is you make the trap anisotropic. It's an harmonic oscillator trap. You take the angular frequency, say, in the z direction, to be much bigger than that in the x and y. That confines the system more in the z direction and introduces this anisotropy. The next thing is to actually excite, okay, I'm almost done, is to excite a mode whose dominant dissipation is governed by the spin 1 kind of component. And in fact, we could solve the coupled equations of superfluid dynamics. It's quite complicated, but in the linear approximation where the amplitude is small, and we identified exactly such a mode. What was more interesting was that this mode is well known in the cold atoms literature. It's called the scissor mode, and this mode is such that the superfluid and normal velocities track each other, and the velocity is such that along the x component, the velocity varies linearly in z, and in the z component with x. So as you can see, if you try to compute the shear, you get a shear component along xz, and that is the spin 1 component in the system, which we hope will become small. And then you just look at the energy loss, the dissipation, and the time scale over that, which the dissipation occurs, which should be sensitive to this component of the viscosity. So that's the basic idea. Now, in fact, this mode has already been seen, and this is what got us excited. Already been excited, this mode has been excited by an experimental group working on cold atoms, the group of Grimm et al. And what they see already is the effect of viscosity. You see that there is a decay in the amplitude here with time, on time scales of order milliseconds, which is due to viscosity. And basically the experiment then is crank up the anisotropy and see if there's a change with this viscosity becoming smaller, okay? Nature has to be kind and so on and so forth, but it's at least well worth looking because they don't have to do much. The time scales are at hand, they've even excited the mode of interest and so on. And so it's just a matter of just driving the system into this regime. There are some caveats. You can't, it turns out, drive the system into extreme anisotropy, but roughly into a regime where the anisotropy is order 1. But if it's order 1, is that big enough? We don't know what, numerically in any precise way, what the corrections are, and so on and so forth. And a few other caveats which I can tell you about. The approximation that the potential is linear is not true, but the dominant contribution to the viscosity comes from a small region of the trap, and it can, but it's not small enough. So again, our general gravity results hold for linear potentials. This is not quite a linear potential. It would be linear if delta z over z were much less than 1, but it can only be made about 0.3 for technical reasons I can tell you about. So there are various caveats, but it seems like something well worth trying to go for. Okay? So bottom line is that this is a kind of system where perhaps if nature is kind, they might see the kind of effect with gravity systems seem to show quite generic. Okay, well, let me end. There is a rich set of anisotropic black-brain solutions in systems consisting of gravity coupled to reasonable matter. This could hopefully shed light on the behavior of some set of strongly coupled anisotropic systems. I don't know, maybe in quasi-crystals and so on. In a relatively simple case, in the relatively simple case where translational invariance is preserved and rotational invariance is broken, the gravity systems already reveal a fairly general and interesting property of the reduction of some components of the viscosity, which we think could be tested quite easily in existing cold atom setups. And if nature is kind, I think that would be really quite an exciting result. I'm going to end with a quote because I think that will tie in with something Spenta has already emphasized from Feynman, who says, nature uses only the longest threads to weave her patterns so that each small piece of her fabric reveals the organization of the entire tapestry. I think this is a beautiful quote for me. I've always held it close to heart. And it's something that Spenta has always, I think, felt in his heart and emphasized. And so I thought I would end with that and wish Spenta here. You can see the similarity from one prophet to another. And I wish you the very best, Spenta.
Questions for Sandip?
One of the reasons why these Rick experiments was inconclusive was because the errors in the measurement, because of the uncertainty in the initial conditions, was as big as the result. So people quoted results of eta over S as 0.1 plus or minus 0.1. So why don't these cold atoms have similar uncertainty in the initial conditions?
First of all, I'm told now at Rick the situation is better. Better now. I'm told they have a pretty good determination of eta over S from their I don't know, but okay. But here the determination of eta in the isotropic case is really pretty good. I mean, there are two ways in which you can measure eta over S in these systems. One is the analog of what you do in Rick, which is you set up a set of atoms and then you release the trap and you see how it expands. And then you model that as a fluid with a viscosity and you extract a viscosity. But the second way of doing it, which is actually what we need, is that you excite the system in a particular mode and then you watch how the energy in that mode decays out. And you can really carry out these measurements quite precisely. As I was showing, they haven't quite done it for the scissor mode, but there's sort of corresponding data, and you simply fit this profile to e to the I omega t minus t over tau and extract the tau. And you can really do that quite precisely, and then it's really the connection between tau and eta is then a linear relation which you can extract. So seems like things are under reasonable control for the isotropic case.
Could you go back to the slide where you had the geometry? Right, okay, so yeah, next forward.
Oh, I'm going down. Oh, cool. I'm sorry. Okay.
Oh, yeah, there. Just one. So omega z, okay. So the idea is you have a trap that's like pancake almost?
Yeah.
Is that right? And then what is the direction you're looking at the viscosity?
Yeah, so it is a pancake, but the reason why we can't make it too isotropic, too anisotropic is if you make it too pancake-ish, then the fluid flow, instead of being 3D, becomes 2D. Right. So that is the limitation.
Imagine the viscosity scissor mode in this direction, like you're cutting the pancake, that's the flow.
You're cutting, yeah.
Z plane, is that right?
That's right. Yeah. So Z is the anisotropy direction, and then your flow is something like, roughly, although I'll show you, is that the velocity along the x direction sort of changes with Z, and that shear. So the velocity was something like Z times x hat plus x times Z hat. And that's the kind of flow, and so you have a sort of shear from here, which then actually is the dominant.
So the TXZ correlation.
Yes, TXZ.
And in terms of the ADS geometry, what do you want the system to do? So you want it to split apart into little pancakes, which is the decoupled direction.
Yeah, the decoupled direction is Z.
Z.
Yeah, Z. So that's right. That's right. You wanted to decouple, but with some coupling enough. You want them to become a pile of crepes with some couplings between them. Yeah.
I have a very simple question. I thought the bound is eta over s is less than 1 over 4 pi, right? The general bound. But somewhere you showed 6 times 1 over 4 pi. That
yeah. So
bigger than. I'm sorry, bigger than.
Yeah, the bound is bigger. Yeah.
Let me profit from asking a question. If you take 3 massless scalar fields and you do exactly the same, keeping rotational invariance, you will find that eta over s, now it's, in fact, it's the same in all directions, goes to 0 as t squared, which suggests that it's not anisotropy which is the issue, but the breaking of translation invariance. Can you?
I see. So you say.
In fact, this is known since the work of Hartnell and others.
I see. I didn't know this actually. So you say you can have isotropic systems,
you can
driven
do exactly
isotropic
what you did,
systems.
Put an axion in each direction with the same coefficient, and then the geometry remains completely rotationally symmetric, but all shear viscosities go to 0 as t squared. They're exactly the same. Yes, but so that's what I'm trying to say, that the issue is not the breaking of rotational invariance, but translational symmetry.
Yeah. That's part of my problem. If you break translational invariance, it gets harder to define transport and
But
so
this
on.
is what you're doing.
Well, here. Yeah. First in the gravity calculations, although we have a linear dilaton, as I was trying to say, really we should think of it as a constant driving force. Here, you're right. Here, so this was one of my caveats. I didn't want to sweep it under the rug. It's not really that you have a constant potential, you have a quadratic potential. But that's one of the reasons why we are not quite, where gravity tells us. But what our hope at least was that you may have the dominant contribution to the viscosity come from only some small region of the trap. And then in that region, you can model the potential as linear. Now, in fact, what happens is you have a parameter, which is how cold is the trap compared to the chemical potential at the center. And it turns out, as you make the roughly the equilibrium situation is it's colder than the phase transition temperature at the center, and then as you go out, at some point you have a phase transition, and then it becomes a normal phase. And if you start at colder and colder temperatures, you can make this width smaller and smaller and localize things. But it turns out that it has to do with the fact that viscosity is small at strong coupling. It turns out in the normal phase, in the broken phase, you have Goldstone modes, and those Goldstone modes can contribute a lot to viscosity. So that's an unwanted component. So if you balance the two, then in the end, you can't have a trap which is where the contribution is very small. So that is another reason why in the end, the experiment doesn't quite mimic a linear potential.
Is there any field theoretic reason why viscosity will be less when anisotropy is present?
I at least don't know. I at least don't know. It's not as simple as this fluid doesn't want to move, because the fluid can move at different values of z with different velocities. And it's not as if we are not trying to move if you were trying to move the fluid in the z direction, of course there's a force against it. You're not trying to do that.
Yeah, and that's what your geometry seems to suggest is happening, right? If it's true that essentially correlation functions are localized in the z direction, then what's happening is that this is like a bunch of three-dimensional field theories with weak interactions between them. Now, viscosity, you can transmit momentum in two ways. Either you can have the momentum carriers moving across the layers, or you can have them interacting by some forces. And I think what's happening here is that the momentum carriers aren't moving very much between the layers. They're interacting by some forces which can then become weak. You just have a bunch of layers of three-dimensional field theories with weaker interactions between them. Automatically, I think the viscosity will be very small.
Yeah, it could be something like this. I'm not sure that's exactly what's happening, because I'm not sure that's exactly what the calculations, whether there's a precise way calculationally that would show this.
Anyway, I suggest that we thank Sandip again.